As I was reviewing your past papers for chemistry, I realized that there is something very important that I have to teach you before you can understand chemistry even more further, which is the topic of what's a molecular formula and what's an empirical formula and how can we balance chemical equations. Because in our previous chemistry classes, we did atoms, molecules and ions, water compound, how we can name binary ionic compounds that are formed by a type of bond between metals and nonmetals, and how we can name covalent compounds that are formed between the bonds of nonmetals. So now that we have that basis, we have to talk about things known as the differences between a molecular formula and an empirical formula, because these questions usually come and we have to learn the different ways in which we can represent a compound. So a compound can be represented via a molecular formula and an empirical formula, all right? So this is what I was saying here. So if you look at this structure here, let me project the notes. Let me project the notes. If you look at this structure here, there are certain ways in which we can represent a compound. So the first way we can represent a compound is just words by using the name. So for example, there we have got an organic compound. We're going to do organic compounds very soon called benzene. We have an organic compound called benzene. So benzene can be represented by just its name there, all right? So this is benzene. But we can also represent benzene in terms of the molecular formula. The molecular formula, which is the actual number of atoms that this chemical compound has. So we can say, all right, benzene, it's C6H6. So we can say, all right, benzene is made up of every molecule of benzene is going to consist of 6 carbons to 6 hydrogens. But what if we want to know the ratio? What if we want to know the ratio? Like, all right, in this compound, what is the ratio of carbon to hydrogen? So to know the ratio of carbon to hydrogen, we use something known as the empirical formula. So the empirical formula just gives you the lowest whole number ratio. For every carbon atom, how many atoms of hydrogen do we have in this molecule of benzene? So that's what the empirical formula does. But the molecular formula tells you the actual number. So how do we find the empirical formula? We just divide by the lowest common multiple. Or in this case, rather, it's not the lowest common multiple, it's the highest common factor. Like you have to ask yourself, all right, what number can go into, what's the highest number that can go into 6 and 6 without leaving a remainder, which would be 6. So the empirical formula will become CH. So these are the ways in which we can represent any given compound. We can write the name, then we can talk about the actual atoms that this molecule has. Then we can talk about the empirical formula, which is the ratio. So here I can say each molecule of benzene, for every 1 carbon, because the ratio is now 1 to 1, for every carbon that exists, there is 1 hydrogen atom, and vice versa. For every hydrogen atom, there is 1 carbon atom. So that's the empirical formula and molecular formula. So molecular formula, it's the actual atoms that are present. Then the empirical formula, it's the whole number ratio. There will be no decimals. So it's the lowest whole number ratio. Lowest whole number ratio. I'll send you these notes just now coupled with this video so that you should understand things better. So let's do a little bit of some practice questions. We have given molecular formulas and we have to figure out how we can get their empirical formulas. So the first molecule is C8H18. So that's the molecular formula there. And then we're trying to figure out how can we figure out the empirical formula, which is the lowest whole number ratio, and it shouldn't have decimal points. So here, the highest number here is 8, but 8 cannot go into 18 without leaving a remainder. If we divide that, it will be a 2.5. So we have to look for a factor that can go into both 8 and 18 without leaving a remainder. That would be 2. So if we divide that by 2, we're going to get C4H9, C4H9. There are no common factors between 4 and 9. So this here will be the empirical formula. So if we were to put it there as empirical formula, C4H9. So remember, this is the molecular formula, which is the actual. So this molecule has got eight carbons and 18 hydrogens, but the ratio is a 4:9. So we're going to say for every 4 atoms of carbon, there exists 9 hydrogen atoms, and vice versa. You can say for every 9 hydrogens, there exists 4 carbons. That's how science is. Science has to make sense. Because if someone tells you, oh, there's a molecular formula and then there's empirical formula, and then all you do is just divide, you just divide, it doesn't make sense. It only makes sense if you follow it in this way. Molecular formula is the actual, then the empirical formula, you have to start dividing by common factors until you reach a state where you cannot divide anymore. So let's look at the other one. The other one is C8H6O4. So here we've got 8, 6, and 4. 2 can go into these once more, right? So we can divide by 2. So if we divide this by 2, we're going to have C4H3
3
O
O2.
O2. Yes, all right. So this will become our empirical formula, the lowest whole number ratio. So the ratio here is 4 to 3 to 2. So they are saying for every 4 carbons, there exist 3 hydrogens and 2 oxygens. Or for every 3 hydrogens, there exist 4 carbons and 2 oxygens. And for every 2 oxygen atoms, there exists 3 hydrogens and 4 carbons. So that's how you read the empirical formula in that way. But the actual is C8H6O4. This one is simple. These questions usually come in MCQs and also in paper 2, and people just start getting scared for nothing. So this is C3N12. Oh my God, we have to do organic chemistry at some point, probably next month. So the lowest number that can divide here is 3, right? We divide by 3 there, divide by 3, we're going to get CN6. So for every 1 carbon, there exists 6 nitrogen atoms, or for every 6 nitrogen atoms, there exists 1 carbon. Let's move on to this one. What's this one? This one is P2S3. So this one becomes a little bit complicated because we have got prime numbers. We've got a prime number there. 3 is a prime number. Because we have got a prime number here, we cannot divide by anything. So at times, the examiner can confuse you. They can bring something like this. You just say the empirical formula or the molecular formula is exactly the same as the empirical formula. this happens, some questions can come like that. So the empirical formula will be P2S3. The empirical formula is exactly the same as the molecular formula. So let's do the last one. Then we move on to balancing chemical equations. We have got H2O2. So this one's easy, right? Just divide by 2. Then we're going to have HO as the empirical formula. So here the ratio is 1 to 1 also. For every one hydrogen, there exists one oxygen, or for every one oxygen, there exists one hydrogen. So HO, let me write the ratios. So this is a 4 to 1. This is a 4 to 3 to 2. That's a 1 to 6 ratio. This is a 2 to 3, and this is a 1 to 1 ratio. In case the question goes beyond and says, what's the empirical formula and what is the ratio from the empirical formula? So the ratios you get from these two transcripts, they are 2 to 1, 2 to 3, 1 to 1, 1 to 6, 4 to 3, 4 to 9. So that's the empirical formula and molecular formula. So definition of molecular formula is the actual number of atoms present in a compound, but the empirical formula is the lowest whole number ratio. And you get it by just dividing by factors until you cannot divide anymore. So when it comes to acids, bases, and salts, when it comes to redox chemistry, when it comes to the mole concept especially, you are going to be given chemical equations. You have to identify what type of reaction it is. You have to be able to write a proper equation with the proper state symbols, and you have to be able to use more ratios to balance, or just molar coefficients to balance the chemical equation accurately. Then you use those molar coefficients to start doing your stoichiometry. They'll tell you to calculate the mass, they'll tell you to calculate the concentration, um, the concentration using limiting reagents. They will tell you to calculate the volume using cubic decimeters or cubic centimeters. So balancing chemical equations is extremely important. So chemical equations come from practically a chemical reaction. So from definition, a chemical reaction is a process in which one or two substances, so you have two sets of substances. For any chemical reaction, you have got reactants, producing products. So you can have A plus B giving you AB. So every chemical reaction is going to have reactants and products. And please, if you can see here, right? A and B, there is still A and B here. There is nothing like a new substance X there. You are still using the same compounds. It's just that sometimes these reactions can be reversible, some of them are irreversible, but the atoms or the elements, and I'm saying this is extremely important, the elements on the reactants are exactly the same as the elements on the products. Everything is the same. It's just the compound combination that will be different from the reactants and the products. And sometimes the reactants or products can be solids, and for solids, you have to say symbol capital letter S. For liquids, you can just put L there, small letter L. For gases, you say small letter G. And if it's dissolved in solution, aqueous solution, if it's dissolved in an aqueous solution, you say AQ for aqueous. The type of reaction is going to guide you. If it's an acid-base reaction, you're going to have maybe some solid giving you a salt and water, and that salt and water will always be in an aqueous environment. but water is a liquid, so you can say liquid. So the type of reaction is going to guide you on the state symbols that you're supposed to use. And this is what I was saying. Stylus. Okay, there we are. Let me use paper. The elements in the reactants are exactly the same as the elements in the products. This is something that's extremely important. Let's see how we can apply that. So there are certain steps that you can follow in terms of balancing a chemical reaction. I highlighted them right here. So when you're getting these notes, you should highlight them also by a highlighter. So there are certain steps. Step one, we have to determine what reaction is occurring. What are the reactants? What are the products? What are the physical states? So for this one, the question is going to guide you. The question is going to tell you whether it's a redox reaction, whether it's an acid-base reaction, whether there is some form of condensation reaction taking place. The question itself is going to guide you. And this is where the state symbols also come from the type of reaction. Then step two, you have to write the unbalanced chemical reaction. So they might say, all right, in an acid-base reaction, sodium hydroxide reacted with hydrochloric acid to give you sodium chloride plus water. Then they say, so after that, you determine, okay, we're describing an acid-base reaction. Then you write the unbalanced chemical equation. After writing the unbalanced chemical equation, you start your inspection. You sort out everything. So now you have to, after writing your unbalanced chemical equation from the question, so you write the unbalanced equation from the question itself, and then you now start inspecting. So you have to balance by inspection, starting with the most complicated molecule. You're going to see this process, and then you now start using these coefficients. What coefficients are necessary so that the same number, so we're trying to get the same number of each type of atoms appear on both the left-hand side and right-hand side. So what's on the left-hand side? So atoms on the left-hand side of the equation have to
Papu, ulimpias alhamdulillah.
atoms on the right-hand side. So the atoms on the left-hand side will have to be equal to the atoms on the right-hand side. And here is a big thing. A balanced equation has the same number of each type of atom on both hand sides. So it's practically saying this. Your atoms on the left-hand side have to be equal to your atoms on the right-hand side. So let's try to apply these steps from these 5 examples. So the first one, I created some form of scenario, but these, we won't talk about the nature of the reactions. They are just based on practice. So here we are saying hydrogen gas and chlorine gas react to make hydrochloric acid. So we have got hydrogen there, hydrogen H2 plus chlorine gas reacting to give us hydrogen chloride, but if it's dissolved in water, it becomes hydrochloric acid. So here, these are all gases, and hydrochloric acid is in an aqueous environment. So we are going to say reactants and products. Then you're going to start asking yourself, all right, what are the atoms? Just the atoms that make up this chemical reaction. The atoms that we have got hydrogen and chlorine. So we're just getting the individual element itself, not the tools there, the prefixes. We're getting the individual elements. So in the reactants, I've got hydrogen and chlorine. Remember, the same atoms on the left-hand side on the reactants have to be equal to the products. So meaning even the products have got hydrogen and chlorine. And then now I start to count. In my reactants, I have got two hydrogens. So I'll say two hydrogens. And here in my products, I've got one hydrogen. For chlorine, we have got two chlorines there, and there chlorine, we have got one. So now we start uh, balancing by inspection. We start to ask ourselves, all right, how can I make two hydrogens there and two chlorines? So you look, let me create some space. Okay, so HCl. So you start to ask yourself, all right, if I place a 2 here, this coefficient, now you know what coefficients are in chemistry. These molar coefficients are any number that's appearing in front of a compound. So our compound is hydrogen chloride there. If we add a number there, it becomes a molar coefficient. So if we add this coefficient there, it's like multiplying. So this 2 will be means there are now two hydrogens there. By adding these two, it means there are two hydrogens there and two chlorine atoms there. So by just adding these two, you cancel this and put a 2 there, and you cancel that and put a 2 there. Then you start comparing. Then you'll be like, all right, I have two hydrogens in my reactants, two hydrogens in my products, two chlorines in my reactants, two chlorines in my product, meaning the equation is balanced as H2 plus Cl2 to give us 2HCl. So this is how we balance chemical equations by inspection. Let's try moving on to the second one, because at least I know if we answer all these questions, balancing chemical equations will be easy for you in any type of reaction. So let's write the second one. We have got xenon plus fluorine to give us xenon hexafluoride. Don't mind the names. Don't mind the names as such. Focus mostly on balance in the equation, because even in the exam, some names, some compounds will be complicated to pronounce. But as long as you've written the correct form, everything will be okay. So we say our reactants. We have got reactants there, and we have got products there. Our reactants, remember, we're writing the individual elements. We have got xenon and fluorine, meaning the exact same thing should appear there. Xenon and fluorine. How many do we have there? We have got one. We put one there. Here we also have one. How many do we have here? Two, right?
Two. Yes.
There we have got six. So
Six.
what number can we add here to balance it? Here, what coefficient can we add here so that we can multiply? 3.
Three.
Yes, exactly. So if we can add a 3 there, we can say 3 times 2. We can
Times
also
two.
multiply like this in chemistry, by the way. This coefficient can multiply with this prefix underneath there. So 3 times 2 will give us 6.
6.
So I've got one xenon there, six fluoride, six fluorines, six fluorines there. So the balanced chemical equation will be Xe plus 3F2 to give us XeF6. So this is balanced. Do you see how to balance chemical equations? It's not that complicated. We just balance by inspection, and we have to use coefficients. And by now, the word coefficient, you encounter it in math, and now you encounter it in physics, but it will still mean the same. In math, a coefficient is a number that appears in front of a variable, but in chemistry, a coefficient will become a number that appears in front of a chemical compound, and it can be called a molar coefficient. So question 3, we have some form of silver there. Silver reacting with, this is an acid. It looks like stuff. Oh, no, it's not an acid. Dihydrogen sulfide. I thought it was sulfuric acid, but this is not how. Sulfuric acid is H2SO4. So this is dihydrogen sulfide. So it's giving us a salt, Ag2S plus hydrogen gas. So we do the exact same thing. We say reactants, products. Then we put our individual elements individually without the numbers, silver, hydrogen, and sulfur. The exact same thing has to appear this side, the other side on the products, silver, hydrogen, and sulfur. Then we have got one there, 2 hydrogens from this, and 1 sulfur. On our products, this 2 represents 2 silvers, so we have 2 there. We have got how many hydrogens? 2, right? 2 hydrogens,
Yes.
and 1 sulfur. So now we start to balance. So here we've got 1 silver, here we've got 2. So where can I put the coefficient there? I can add the coefficient here, right? Like so. So this 2 there means we now have 2 silvers.
2 silvers.
Yes.
Yes.
All right. Okay. I was hearing my own echo there. So this coefficient there means we now have 2 silvers. So we can cancel that and put a 2 over there. So we've balanced the silvers. Oh, this was actually simple. Putting the 2 there has actually balanced everything. So I've got 2 there, we've got 2 there, 2 there, 2 there, 1 there, 1 there. So the complete reaction just becomes 2Ag plus hydrogen sulfide to give us Ag2S plus H2. So maybe this reaction, this looks like a redox reaction of some sort. Remember, the question guides you. So if I were to put theoretical state symbols, silver is a solid. This was probably in aqueous environment. This was in an aqueous environment, and hydrogen is a gas, theoretically, but because we don't know what question came. So let's try to balance question 4. By the way, you should practice. So when I send you this video, you should practice this. Practice how to balance chemical equations, because it's a very, very important skill for anyone taking undergraduate O-level chemistry. So this one says potassium hydroxide plus carbon dioxide to give us potassium carbonate plus water. So this is a hydroxide is obviously in aqueous. This is a gas. This definitely aqueous, and water is a liquid. So we say reactants and products as usual. Then we target the atoms. We have got potassium, oxygen, hydrogen, carbon. Potassium, oxygen, hydrogen, carbon. We won't say oxygen again. We've already counted it there. The same things, we should have them in our products. Potassium, oxygen, hydrogen, carbon. How many potassiums do we have? 1.
1.
Excellent. How many oxygens do we have here?
2.
What about this one?
1.
Plus 2, so it's 3. 3 oxygens in the reactants. Then how many hydrogens? We have got 1, right?
1. Yes.
How many carbons? We just have this one here, so 1. We go this side. How many potassiums? 2, right? How
Yes.
many oxygens?
3.
What about this one?
0. 3.
It's an oxygen, so in total we have got 4 oxygens. So 3 plus this one, 4 oxygens. Then hydrogens, we have got 2. Carbons, we just have this one here, this one there. Okay, so now we start the balancing process, right? So from here, with my pen. Right. So here we've got 2 potassiums there, and we want 2 potassiums this side also. So we have to add a molar coefficient in front of this compound there, potassium hydroxide. So adding these 2 here changes things. How does it do that? It changes the number of potassiums to 2, meaning now we have got 2 potassiums, but we also have 2 oxygens. We also have 2 hydrogens. So most of the things here will change. The number of oxygens will change. Since now we have got 2 oxygens here, 2 plus these 2, we now have 4 oxygens instead of 3. You've seen that, right? This molar coefficient means we have got 2 potassiums, 2 oxygens, and 2 hydrogens, like we're expanding. So since now we have 2 oxygens in this compound there, potassium hydroxide, and we have got 2 oxygens in carbon dioxide, we now, meaning by in total we now have 4 oxygens. Then how many hydrogens do we have? We don't have 1 hydrogen anymore. We have got 2 hydrogens, right? Remember this coefficient there, it expands the whole compound. So we now have 2 hydrogens. How many carbons do we have? We still have 1. So 2, 2, 4, 4, 2, 2, 1, 1. As easy as that, it's balanced. So the balanced chemical reaction, chemical equation will be 2KOH plus CO2 to give us K2CO3 plus water, state symbols, liquid, aqueous, gas, aqueous. That's how you balance chemical equations. The last one is so simple. Please practice this, watch this video so that things just go very easily. Let's balance the last one quickly so that we can end our day. I'm sure you want to end your day, and I also want to end my day. This week has been busy. Sodium plus chlorine to give us sodium chloride, like so. Sodium is a metal on the periodic table, so it's a solid. Chlorine is a gas, and sodium chloride will be in an aqueous environment. Reactants, as usual, same thing. Reactants, products. We have got 1 sodium, 1 chlorine. Same thing this side, sodium, chlorine in terms of elements. Here we've got 1, here we've got 2, here I've got 1, there I've got 1. So the only molar coefficient I should add is here, so that it expands. But if I add it there, it will expand like that, right? meaning we're going to have 2 sodiums and 2 chlorines. So this is balanced, but this sodium is not balanced. So we're going to add a molar coefficient there so that we can have 2. So the balanced chemical equation will be 2Na plus CH2 give us 2 sodium chloride, aqueous gas solid. So this is how you balance chemical equations, and that's how you determine the molecular formula and the empirical formula. I have a class at 17 hours teaching methodology diploma. I'm now doing a diploma course in teaching methodology to just, because all lecturing jobs require someone to have a diploma in teaching methodology. So I have class at 17 to 19 hours. I will see you tomorrow for mathematics so that we can finish that graph that we started. That one that's curved, it was an exponential graph. All right, have a good day, end of the day. I will see you tomorrow.
Okay. Okay, same to you.
All right, bye.